Okay, good morning, everybody. In connection of summer training school under DBT Star College scheme, Government of India, today on the 8th day, it is our opportunity and privilege to have the glorious presence of Dr. Rajarshi Ghosh, Associate Professor, Department of Chemistry, the University of Baroda. Today, he will deliver lecture on magnetic interactions in dinuclear transition metal complexes and Prussian blue analogues. It is for your kind information that the history of magnetism starts earlier than 600 BC, but the initiation of conceptual understanding dates back only in the 20th century, after which the scientific community started developing technologies based on this understanding. The phenomena of magnetism was most likely first detected in the mineral magnetite, also called lodestone, Fe3O4, which is essentially a chemical compound of iron and oxygen with inverse spinal structure. The study of the magnetic field in different materials helps us to rationalize various fundamental effects and phenomena. As our topic of discussion today, the magnetic interaction in transition metal complexes. So for example, I prefer to state that the study of magnetic properties of transition metal complexes has provided a beautiful insight of stereochemistry of metal centers and the nature of metal ligand bonding. So to have a detailed look, we must be attentive to our lecture today, which will be delivered by Dr. Rajarshi Ghosh, who basically teaching this magnetochemistry during the last 10 to 15 years and also carrying research works in this field. So before inviting him, I would like to share a very few words about his CV. Dr. Rajarshi Ghosh obtained his MSc and PhD from University of Kolkata and the University of Baroda respectively. He joined the Department of Chemistry, the University of Baroda as a lecturer in 2008. Now he is Associate Professor of the same department in the same institute. His research interest covers synthetic coordination chemistry, magnetism, bio-inspired catalysis, biological inorganic chemistry, etc. 7 students have received their PhD under his supervision. Besides these, he is also interested in science popularization. He received Jogomaya Bosu Memorial Award by Bongio Bigyan Porishod in 2020 for writing science in regional language in Bengali actually. With these brief introductory words, I wish to hand over this platform to Dr. Rajarshi Ghosh to start his talk. Sir, please start your lecture. Over to you.
Thank you, Dr. Shamanto, for this nice introduction. First of all, I would like to thank the organizing committee of this school, particularly Dr. Samanta for the course coordinator of the program, and Dr. Misra, the principal of the college and the chairperson of this program, for providing me such a nice opportunity to share some of my thoughts and views amongst the undergraduate and postgraduate students of the different institutions of our country. So before going to start my lecture, I would like to say that magnetism nowadays is not only a very important topic in chemistry or physics or mathematics, but also it is now being popularized in biology, because you know a lot of biological molecules, including hemoglobin, myoglobin, etc., these are paramagnetic, and magnetism, it is said nowadays that magnetism has a profound effect on human health. So with this background, I have chosen this topic for the deliberation in this present school. And actually, today we will discuss one very important aspect of molecular magnetism. You know, so molecular magnetism means magnetism of the molecules. Previously, physicists study magnetism with the inorganic solids which were infinite in their direction. But after the discovery of coordination molecule and after the gradual development of the magnetism, it is now being studied by the inorganic chemists in the way that the molecules, that means the coordination molecules, are itself behaving like a magnet. Okay. So we will see that in this present discussion, we will not at all consider any intermolecular type interaction. Only the magnetic interaction inside the molecule between or among the different paramagnetic centers, which will be obviously metal centers in my present discussion, will be discussed, will be elaborated. And one more thing, in this discussion, the coordination molecules, what we will take, the nuclearity of these coordination molecules will be restricted to 2, not more than that. That means the molecules with 2 paramagnetic metals will be discussed, not the nuclearity of not the molecules with a higher nuclearity will be taken into account for today's talk. So I'm just starting my lecture, and so I'd like to share the screen. Okay, so just a minute. The students, can you see my screen?
Yes, sir, it is visible.
Okay, okay. Is it fine to all of you?
Yes, yes.
There is one box is coming in the right side of the screen in my computer. Is it there with your screen? Is there any?
No, sir.
Okay. Then it's fine. It's fine. I do not know. I can. Okay, leave it. So I'm starting. You see, the title of my lecture, as it is already mentioned, the magnetic interactions in dinuclear metal complexes and push and glue analogs. So my lecture has a 2-part basically. One is the dinuclear transition metal complexes, their magnetism, and the compounds which are known as the push and glue analogs. Those will also be discussed. So I am starting. You see, before going to the core of my lecture, I will just tell something about these are the d orbitals. Okay, perhaps you all know these d orbitals. These are just a minute. This dialog box is making some problem. Okay, so these are the d orbitals, but we have. I do not know how can I hide this. Is it possible?
Please, full screen, exit full screen.
How can I go there? How can
view
I
in view option? Please see in the view option. View option. View option.
Okay, just a minute. Mute so participant chat. Full screen.
Exit full screen.
Oh, exit full screen.
Yes, sir.
To exit. So where is it, Dr. Samanto?
In the view option. In the view option.
The view option. I do not find the view. কোথায় মানে উপরের দিকে কোথাও থাকবে?
হ্যাঁ, উপরের দিকে স্যার। You are viewing admin screen. উপরের দিকে একটা দেখুন, একটা আসছে।
উপরের দিকে আছে মিউট, স্টপ ভিডিও, পার্টিসিপেন্ট চ্যাট, নিউ শেয়ার, পজ শেয়ার, অ্যানোটেট, রিমোট কন্ট্রোল, আর একটা আছে মোড। মোডটা খুলে দেখবো?
হ্যাঁ, মোডটা দেখুন তো স্যার।
মোডে আছে হাইড নেমস অফ অ্যানোটার্স, হাইড ভিডিও প্যানেল। এইটা কোথায় হবে?
হ্যাঁ, হাইড ভিডিও
প্যানেলটা করে দেখবো?
হ্যাঁ স্যার, ওইটাই আপনাকে গার্ড করতে।
হ্যাঁ, ঠিক আছে। এবার ঠিক আছে আমার ক্ষেত্রে।
হ্যাঁ, ঠিক আছে। হ্যাঁ,
ফাইন।
ঠিক আছে।
সো just a minute. Yes, these are the d orbitals. Okay, what I'm telling before going to the core of my lecture, as I told you. So I shall talk something about this d orbitals. Okay, so these are the 5 d orbitals. I know students are very much familiar with these figures as they go through this kind of d orbitals in their standard textbooks. And here in this 3 dimension, okay, this is the dxy. That means the orbital in its xy plane. It is dyz. That is, this orbital is in the yz plane, and this is the double shaped, you know. And there is one thing. There is the symmetry of the d orbital, which is also very important. But today I'm not going to that kind of. Just a minute. I'm switching off my mobile. Otherwise, it may create disturbance. Just a minute. Yes, it is done. Okay, so these are the dxy. These are the symmetries. One thing is there. There is a symmetry of the orbital. You know, this white colored shaped dumbbell. The symmetry of this white color shaped double dumbbell, has exactly opposite symmetry to that of this shaded double dumbbell. Okay, so I'm not going to the details of the symmetry because this will take much time and this will not be very much relevant for today's discussion. Okay, so I will tell something others. Just I'm coming to that point. So this is a dxy orbital. So this dxy means the orbital is in xy plane. A dyz orbital, this is in the yz plane, and this is the zx orbital. This is in the zx or xz plane. Okay, and the orbitals are in between the axis. Okay, this is the reference frame, the left hand side, what I have shown. Okay, so this is the x-axis, and the vertical axis is the z-axis, and the horizontal axis is the x and y-axis. Okay, so this is dx square minus y square orbital. This kind of orbital is something different from the rest 3 because here the lobes are along this axis. It is along x-axis and along y-axis, and the names of the orbital is dx square minus y square. And you know, these functions written just in the subscript of d, that is x square minus y square, xy, yz, zx. These functions actually help a lot to find out, you know, this symmetry of the orbitals. Though I'm not going to that part today. So the last orbital is the dz square. This is most interesting because the shape is something different from the other orbitals in these 5 sets. Okay, so what happens here along z-axis? It is shown that an double dumbbell is there, and here is a round-shaped shaded area around this double dumbbell orbital along the z-axis. This is known as the dz square orbital. Actually, what happens? This z orbital, this has actually 2 lobes. Okay, the 2 lobes along z-axis are eclipsed. That means exactly overlap one lobe on the another, and that's why it looks like a single lobe, but it is actually 2 lobes are there. And along the x-axis and y-axis, in both its positive and negative direction, 2 lobes are there. That is double dumbbells are there. So all these double dumbbells along this x and y axis are all together written in this way in the shape of a circle, and it is black shaded because symmetry of these double dumbbells along this x and y axis are just opposite to that of the lobes along this z axis. So this is called the dz square. Now from these, what I wish to convey that the names of the d orbitals, what you have seeing here or what you have shown in your textbooks, these are like this: dxy, yz, zx, x square minus y square, and dz square. You all know this. But the fact is that the names of the d orbitals are not absolute. This is a very important thing. What I mean, I can cite an example. Suppose I am known to everyone as Rajoshi in my office. My students, my colleagues, my friends at my working place, they know me as the name Rajoshi. But when I come back home, my mother, my sister, you know, my friends in my locality, they know me in some other name. That is, me being the same person have different names at different positions. The same thing happens with these d orbitals. That means if you just change the position of these d orbitals, d orbitals will change its name, keeping its basic character same. Okay, so you should remember that what dxy, dyz, dzx, x square minus y square, dz square you are seeing in this, in this page, the names of the d orbitals are not always, these kind of things. These may change on changing. This may be changed on changing the position of the orbitals and the reference frames. Now I am giving you one example. That is, you see, this is the, in the left hand side you can see, this is a dx square minus y square orbital. Okay, what I have shown here, that is the axis along y axis and along x axis. But you just make a rotation of 45 degree. Okay, just a rotation of 45 degree. Just to make a rotation in the anti-clockwise direction with the ligands, with the axis at 45 degree. When what happens? The shape of the orbital will be like this. Okay, so now this orbital is not the dx square minus y square now. It is now the dxy orbital. Okay, so the orbital dx square minus y square is being changed to dxy just by changing, just by making rotation of the axis by 45 degree, or just by changing the position of the orbital. Okay, সবাই শুনতে পাচ্ছেন তো? সবাই কি শুনতে পাচ্ছেন?
Yes sir. হ্যাঁ yes sir.
ঠিক আছে. Now next, I'm just what happens, I'm just changing the reference frame. Okay, now in the previous slide you had shown that the reference frame there, the z axis was the vertical axis. Okay, and the horizontal axis was x and y. And the present case, what I'm showing, the vertical axis is the x axis, not the z axis, but the horizontal axis are z and y. Now see, what is the effect of this changing the reference frame on the orbitals? Okay, so the orbital in xy plane, okay, in this plane, xy plane, it is dxy as it was in the previous case. In the yz plane, it was dyz. It is written as yz by mistake. Okay, it will be dyz, and the orbital in the zx will be the dzx. Okay, and the orbital along this y and z axis is dz square minus y square. What it was in the previous case, the orbital along this x-axis and y-axis, it was dx square minus y square. Okay, in the same way, here you see the x and y was the horizontal axis. Okay, in the present case, y and z is the horizontal axis, and so just as it was in the previous case, the lobes along x and y axis was named as dx square minus y square, and in the present case, lobes along z and y axis are now named as dz square minus x square. And what about the last one? This was also as it was in the previous case. In the previous case, it was plotted along the z-axis. Okay, the z-axis, the lobes along the z-axis was the orbital with the lobe along the z-axis was named as a dz square. And here, the orbital with the lobes along this x-axis and all other lobes in along this z-axis and y-axis. Okay, these are all together is named as dx square. The similar kind of orbital in the previous case was named as dz square. So from this, what I can conclude that the orbitals are changing. What I told you earlier, the orbitals are changing their names on changing their positions and on changing the reference frames. Okay, so these things I think you should clearly understand. Otherwise, not only in magnetochemistry, but also in different spectroscopical aspects will not be very much clear to you. So this is very important. And now I will start my discussion on magnetic interaction. The basic thing in magnetic interaction is that, so this equation is very much basic. This is a very popular and very familiar equation, you know. I think physics, chemistry, mathematics students, they know this equation very well, particularly the physical chemistry students. I think they have studied a lot with this equation. And what is this equation? This psi total. I mean, a orbital has two parts. One is the space function, another is the spin function. We can tell it in this way that orbital, the electron in the orbital should occupy a space. That is, the orbital should have a space function, and the electron in that orbital should have a spin. So on combination of these two, that means a space and spin, a orbital is actually formed. And the space part, there is a orbital as a whole is a mathematical function, and the space part, it is also another function which is written here as a psi orbital, and the spin part as a psi spin, it is written as there. And the total function is actually the multiplication of these two terms. That is a orbital function, that is a space function, which is multiplied by the spin function. And the result of this multiplication is the psi total. That is the total function of the orbital. Here we are discussing about the magnetic orbital. That means the orbital having a single electron is known as the magnetic orbital, because this orbital will interact with the other paramagnetic centers to give different magnetic phenomena. Now, what about this equation? According to Pauli's rule, you know, the famous scientist Pauli, physicist Wolfgang Pauli, he actually told that this total function should be always anti-symmetric in nature. There's a lot of simple mathematics with which we can easily prove these things. Okay, so I'm not going to that mathematical part. I'm just qualitatively, I can easily tell that if the total function is antisymmetric, according to Pauli rule, according to Pauli principle, if it is antisymmetric, then either of these two functions should be antisymmetric in nature. That means if psi orbital, you can see I'm taking my cursor on this psi orbital. If psi orbital is symmetric, then psi spin should be antisymmetric. Okay, and on the reverse, if psi spin is symmetric, then psi orbital should be antisymmetric in nature. So these things can be very easily understood with the help of diagrams. Okay, so you see, these are the two orbitals where you know, this is dxy, this another is also dxy. These two are in the, you know, two metal centers. As I told you that I will discuss only the diamagnetic dinuclear molecules. Okay, and these two orbitals are symmetric. Okay, so if these two orbitals are symmetric, then what happens? According to Pauli principle, this spin function must be antisymmetric in nature. This spin function must be antisymmetric in nature. Okay, so what will be? The spin functions will be this way, the antisymmetric. Okay, so what happens? This will result in the antiferromagnetic interaction. Very simple. It is very simple to understand. And because these two spin in the adjacent centers are in the in antisymmetry, that is in the opposite spin, and this will create the antiferromagnetic interaction. Okay, and with this this will result in the lower ground state spin with respect to the system where the ferromagnetic interaction will be there. Why? Because in this part, suppose it is plus up, and as it is in the reverse direction, the spin will be minus up and the total spin will be 0. Okay, so the total ground state spin of this system will be 0. Now, what happens with this system? Here, this orbital and that orbital, these two adjacent orbitals are antisymmetric. Okay, so according to Pauli principle, if the orbital functions are antisymmetric, the spin functions must be symmetric. Okay, so you see, these are the spin functions, these are symmetric. So what kind of magnetic interactions will be resulted? The magnetic interaction will be ferromagnetic in nature. And here, in this case, the ground state spin will be quite higher. If it is plus up in the left part and it is also plus up in the right part, so the total spin is 1. So the ground state spin will be higher in this case. Okay. So this is the very basic aspect of this dinuclear magnetism of these dinuclear molecules. Okay. Now I am going to the actual example. This is actually work of Professor Olivier Kahn. You know, it is O. Kahn. It was a long back in 1983. He published one JSCS paper, which was very important and very fundamental, I think, in the field of magnetism. And from these examples, we'll try to understand the basic underlying mechanism of magnetism in this kind of molecules, the theoretical foundations, the theoretical basics of the experimental results in magnetism with these molecules. Okay. So firstly, these molecules, this kind of molecules have, Professor Kahn actually solved the structure of these molecules. And it was, you know, from after the X-ray, after the solution of the X-ray structure, the two metal centers had been found with two different, geometries. This was square pyramid, okay, and this was octahedral. A copper having its 5 coordination number. Usually it has a tendency to have two kind of geometries. One is square pyramid, another is trigonal bipyramidal. But there is one parameter that is tau. So that parameter actually determines, the value of tau determines whether the geometry will take square pyramidal or trigonal bipyramidal. Okay. So that's another issue. So this geometry of these metal center is square pyramid, and geometry of that metal's iron center is octahedral. Now next we have to fix the reference frame. Okay, so what kind of reference frame is there? It is, you know, this way. It is a general custom in science and chemistry in particular. The metal centers are generally assumed as a z-axis. Okay, so here it is z-axis, and another two, the horizontal axis is the z-axis and the y-axis, and the vertical axis is the x-axis. Somebody have to mute among the participants. Please mute. I do not know.
Participants, please mute yourself. Participant Dibyendu, please mute yourself.
The error is coming, noise is coming.
Okay.
Okay. Now this is a YZ plane. This is the reference frame what we have fixed, and with this reference frame, the molecule, just imagine the molecule is lying in this YZ plane. Okay, as the molecule is lying in this YZ plane, this OCH3 and this OH2, these two are the above this YZ plane, and the Cl is below the YZ plane. Okay, now the next task is to find out the point group of the molecule, because symmetry is very important in assigning the magnetic phenomena. Okay, so the point group of the molecule, there is no much symmetry in this molecule, and this molecule should have the point group, you know, CS. Okay, so C1 is there. C1 is everywhere, and that way C1 is there. And one, reflection plane, which is parallel to this computer screen is there. And with these symmetries, the point group of this molecule is CS. But the problem is that with the CS point group, it is very much difficult to elucidate the magnetic phenomenon of this molecule. So if we just forget about these OCH3, then the molecule easily can have a C2V point group. Okay. So this was Professor Kahn. This is not actually the assumption of mine. This was Professor Kahn who told who assumed this molecule C2V instead of CS. So I have just quoted the line from the paper. Though the point group of the molecule is CS, but Professor Kahn wrote this point group, that means the CS point group, but not too far from C2V. So this molecule is considered as having point group C2V. Now, our next task is to find out the magnetic orbital at each metal center. So how can I do that? We can do that with a very easy and smart way. Just we have to find out the d orbital splitting of the metal centers. Okay. So in the copper part, I will explain the splitting in the copper part. So there, it has a square pyramidal geometry, you know. So this square pyramidal geometric pattern, I mean the splitting pattern, this splitting pattern, I'm sure this is something different what you have shown in your textbooks. The reason is that the reference frames, what the authors of the textbooks use is something different, which I have used in this present presentation. Okay, so this copper center, that is the square pyramidal center, shall have this kind of splitting. The splitting, you can very easily understand this if you draw the geometry. Okay, so you see these are the axes. This is Z axis. Okay, the metal is here. This is Y axis. This is X axis, as I have shown in the left hand side. Okay, and the ligands are approaching in the square plane is in the YZ plane. Okay, and this cone of this pyramid is along this X axis, and the four ligands are approaching in between the axis, and that's why the orbital, which is you know, in between this Y and Z axis, will be the most distable. Okay, because these orbitals, that is the dyz orbital, I have written here just yz, just to make it simple. So the orbitals in between Y and Z, that is the dyz orbital, these will face the ligand head on. That's why these ligands in between the axis Y and Z axis should have will suffer most. That is, the YZ orbital will be the most distable orbital. And next to this, you see this orbital along this X axis, which is X square, I mean dx square. And the one ligand is coming from the upper part, no ligand from the lower part, as the geometry is square pyramidal. So this dx square is also facing head-on interaction with the ligand. As there is only one ligand, so the interaction will be quite lower, and the stability will be quite higher. That is, energy will be quite lower with respect to this YZ. And next to this, the Z square minus Y square, which are lying along this Y axis and Z axis, this will suffer quite lower interaction because no ligand is approaching head-on along this Y and Z axis. The ligands are coming in between Y and Z axis. That's why the dz square minus Y square will be suffer some lesser amount of interaction, and the orbital will be placed in here as I have shown in the diagram. And the rest two orbitals, that is dxz and dyz, these two, this is dxz plane and this is the dyz plane, dxy plane. So these orbitals have lobes in these two planes, which are something different from the lobes in the dyz. Okay, that means the ligands are approaching, 4 of the 5 ligands are approaching along YZ plane, and only one ligand is approaching along the x-axis. That means only one ligand is coming through this xy and this xz plane. That is why these xy and xz orbitals will be suffered minimum amount of interaction, and these two will be the highest stable orbitals in this very geometry. Okay, I think it's very easy. If you just see the molecule, if you imagine the molecule, and if you try to explain the orbital splitting, I think you can do it. Please do not try to match this splitting with the textbooks, because the reference frames the authors used in the textbooks are something different the reference frame what we have used in this present slide. Okay, and as it's a copper, D9 system, so we'll just arrange the 9 electrons here in this present diagram. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So one electron, the single electron in the YZ plane, and I have already told the orbital with having single electron will be called as a magnetic orbital. So this is the magnetic orbital of the copper system in this very molecule. Now, what about this iron splitting? It is an octaedral geometry, you know. This octaedral splitting, I think the students are most familiar with this kind of splitting. And now this is the splitting of the square pyramidal part, what I have just now explained. This B2, I will explain this B2 just now. Okay. Now, what about this splitting of this, you know, iron part? Okay. In iron, here, sorry. And these how can I, here's one dialog box is still coming. Just a minute. I do not know how. It's okay, okay. So this is the octaedral splitting pattern, what I have shown here. And I'm sure this pattern is also something different, what you have shown in your textbook, okay? To make it understand, you have to know the octaedral geometry. Okay, this is the geometry, octaedral geometry, and the reference frame is like this, what I have shown here. And you see, in this very present diagram, this plane, this plane of this octaedral, the square plane, or whatever, which is lying in this YZ, and other ligands L, these are lying along this x-axis. Okay, so the ligands are approaching here in this presentation, in this diagram, ligands are approaching in between the axis, and that's why the orbital, I mean, in this YZ plane, that means the dyz orbital, again in this case, will suffer most. Okay, so here it is shown. So along with dyz, another orbital which is lying along x-axis, and here also two ligands are coming along this x-axis. So the ligands along the, so the lobes or the orbital which is along this x-axis will also be most suffered, will also be most interacted. So these two orbitals, dyz and dx square, will be the most destable in this very present case. And next to this, dz square minus y square, that is along this z axis, these are not facing head-on interaction. Ligands are coming in between these axes, so the energy will be quite lower. And the other two orbitals which are in other planes, that is in the xz and is a xy plane, and here only two ligands along x-axis. These are also not along with the lobes. Okay, and these are coming in between the lobes, are approaching here, and so the energy of these two orbitals will be the lowest in this very particular geometry. Okay, so this is the octaedral splitting pattern what I have shown if the reference frame is taken as it is shown in this slide. Now we have to determine, so here you see in the left hand side, that is in the copper center, the B2 is the the magnetic orbital, and here in this in this case, in this iron 3 center, okay, so these 5 orbitals, each of the 5 orbitals are having a single electron. So all these 5 orbitals are magnetic orbitals. Now, how to determine how to determine the symmetry? We have to determine the symmetry of the orbital. Dr. Samanto, এই উপরে না একটা যে কালো মতন ইয়ে আসছে কন্ট্রোল প্যানেল মতন, ওটাকে কি কোনোভাবে রিমুভ করা যায়?
উপরে মানে আপনার আপনারা
দেখতে পাচ্ছেন স্ক্রিনে?
না না, আমরা দেখতে পাচ্ছি না।
ঠিক আছে, তাহলে ঠিক আছে। So now we have to consider the character table of C2V. Okay, so this is the C2V character table, and now you can see this is the, as the whole molecule have the C2V symmetry, C2V point group. So we have to consider the C2V character table, and with this YZ, you see this YZ have a B2 symmetry. Okay, so it is written as B2. I mean, B2, you have to keep it in mind when we will designate the symmetry. We will have to use these lowercase letters, and when we will designate the state, energy state, magnetic state, or whatever, spectroscopic state, whatever, these should be written in capital letters. Okay, so as it is a symmetry of the orbital, so it is in lowercase letters, and it is B2. Now we see this is XY. This XY has a A2 symmetry. You see, as it is A2 here. XZ, you see, XZ has a B1 symmetry. Z square minus Y square orbital. Z square is here, Y square is here. So this should have a A1 symmetry. And DYZ, this YZ has a B2 symmetry, and another is the DX square. Okay, these have a B1 symmetry. Okay, these are all about the symmetries of these 2 orbitals. And now here also we will just arrange it's a iron 3, so 5d electrons will be there, and we have arranged the 5d electrons in this way. You can naturally you will ask the question why the this electron is written as in the in some inverted manner, in inverted fashion, lower headed fashion. This has a meaning. Okay, I will just come to this point, but initially you can think that this spin is just in the upper headed as it is in other 4 orbitals. Okay, now we have to find out the magnetic state. So the magnetic state of this copper part, now we are actually assuming this as the 2 isolated parts. Okay, so no magnetic interaction is still being considered. These 2 are the 2 isolated states. And with this, the magnetic state of the copper part, it is a B2. Why it's B2? Because the magnetic orbital containing the single electron, 1 magnetic orbital is there, and the symmetry of the orbital is B2. So the magnetic state is also B2. Okay. So the spin of it has a half spin. So symmetry. So 2 into S twice S plus 1. If the S is half, so 2 into half plus 1, so it will be 2. So the multiplicity will be 2. And what about the spin state of this iron part? The magnetic state is, you have to calculate this magnetic state as just by multiplying, these states. This is A2, okay, A2, then B1, you see, this is a B1. And this is multiplied by again A1, okay, then again A1, and again B2. Just if you make the multiplication of these rows, okay, that is A2 is multiplied by B1, A2 is multiplied by B1, then you will see, and the resulting the resulting numbers, this will be again multiplied by A1, and the resulting numbers will be again multiplied by A1, and then if it's multiplied by 2, you will see the state, the row you obtained will be similar to the row of the A1. So the magnetic state of this iron 3 center is A1. Okay, I think if you cannot understand this, I can make it you clear after the talk. Okay, I can show you the calculation. It's a very simple calculation. And here, these 5 electrons are there, and in this electron, in this which is in the down-headed fashion. I have told you that you can assume it is the upper-headed. So the 5 electrons are there, and so the total spin is 5 by 2. 2 into 5 by 2 plus 1, that is 6. So if these iron 3 and copper 2 are assumed as two isolated systems, if no magnetic interaction is being considered, then the magnetic state of this iron 3 will be 6A1. Okay. Now we have to study the magnetic interaction in this very present case. Okay. What happens? This B2 will interact with, this A1. So we'll remind the Pauli principle, where it is told that where it is told that if the orbital's symmetry is different, okay, to make the psi total antisymmetric, if the orbital symmetry is different, that means antisymmetric, the spin symmetry should be same. That is, if the orbitals are antisymmetric, interacting magnetic orbitals are antisymmetric, the spin functions will be symmetric. So here this B2 and A1, naturally the orbital symmetry is not same, it's different. So the magnetic interaction, the spin symmetry will be same, and the magnetic interaction is ferromagnetic. And in the next case, it is also same. That is, it is orbital symmetry is B2, and here the orbital symmetry is B1. That means the orbital symmetry is different. So spin symmetry must be same, and it is a ferromagnetic. And then it is a V2 A1. Okay. So this is the this will also be the ferromagnetically interacted. And next here, this is also ferromagnetically interacted because orbital symmetry is different. So spin symmetry must be same. But here, you see, the orbital symmetry is different. I'm sorry, orbital symmetry is same. It is B2. So the spin symmetry must be different. That is, this anti-ferromagnetic interaction will play in between this orbital and that orbital, this magnetic orbital of copper 2 and that magnetic orbital of iron 3. So this one anti-ferromagnetic interaction is there. Okay. Now we have to consider the ground state spin. How can we calculate the ground state spin of this very molecule? Now, if you forget about this antiferromagnetic interaction, that means if you just think about this is a simple assembly of a copper 2 and iron 3, no magnetic interaction is there. Okay. So in that case, there is one, in the right part, 1, 2, 3, 4, 5, 6, total 6 electrons are there. That means total 6 electrons, if these are considered as isolated system, we will not consider any antiferromagnetic interaction. We are not actually considering any magnetic interaction. So no case of antiferromagnetic interaction and no case of spin inversion will be here. So all the electrons, that means total 6 electrons in total with the copper 2 and iron 3 centers should have a plus of symmetry. So the total should have the plus of spin. So the total spin of the system will be 6 into half, that is 3. So the multiplicity will be 2 into 3 plus 1. Okay. So it should be 7. Okay. Now, but if we consider the actual system, that means if we consider the actual, interaction, not assuming the system as a simple assembly of the two paramagnetic centers. Considering all the magnetic interactions, what we can tell, the total spin in the right hand side is a plus up, plus up, plus up, plus up. So 4 plus up spins are there. Okay. And here it is minus up, and the right part it is plus up. So this plus up and this minus up will cancel out. So total 4 electrons with plus up spins are there. So 4 into half, 2. So the multiplicity will be 2 into 2 plus 1, so 5. So this will be the quintet state. So these kind of 2 probabilities of ground state spin is possible here. Now, I have already told in my previous slide that the spin state, the antiferromagnetic systems actually occupy the lower ground state spin. Okay. So here is two kind of spins are there. One is spin multiplicity 7 and 5. And if the multiplicity is 7, the compound is expected to have completely ferromagnetic system. And if the system is 5, the compound should exhibit antiferromagnetic interaction, because the antiferromagnetically interacted metal systems are always have a lower ground state spin. And now see what experiment tells. From the experiment, you can see this is the experimental result of Professor Khan, where this copper 2 and iron 3 having this molecule, what I have shown in this work, and on lowering the temperature, you can see the magnetic susceptibility is being decreased, which is a complete signature of an antiferromagnetic interaction. So the molecule should behave as antiferromagnetic. Okay, so the quintet state, what we have predicted, okay, considering this interaction, is the correct. So these behavior, the magnetic behavior, what we have predicted from this theoretical foundation exactly matches with the experiment. And this was shown by Professor Khan long back in the year 1983. So the magnetic interaction paths can be, written as in this way. This is the 2d2 and 6-1. This kind of antiferromagnetic interaction is in operation in this very molecule. In the same 1983 JSS paper, Professor Khan showed another molecule that is which contains copper 2 and chromium 3. And we are fortunate enough, because this copper 2 is a square pyramidal, it is not a it is a square planar, it is not a square pyramidal. That's why the point group of the molecule is C2V. We do not have to take any approximation for considering this point group. Okay, this molecule is exactly, this molecule have exactly C2V point group, and the molecule is lying just as in the last case in the YZ plane, and these water molecules are vertically along this x-axis in the upper and lower portion of this plane. Okay, and this is a splitting of the copper. The splitting is same as it was the splitting of the square planar geometry. Okay, the splitting is I think in the way what I have shown for the square pyramidal splitting and octadal splitting, if you consider the orbitals in that way, you can easily understand the splitting also, because the same way, the same approach we have taken to make this orbital splitting diagram of the square planar geometry. Okay, so here also this YZ will be, I'm not going to the very details of this discussion. And here the YZ is a magnetic orbital containing the single electron, and the symmetry is B2. Okay, now what about this chromium 3? This chromium 3 has a this is octadal geometry, and the octadal splitting we have already discussed in the last 1 or 2 slides back, and the similar kind of splitting is there, and the symmetry is derived from this character table of C2V, same way as we did it previously. And the magnetic state calculation, this is also very easy, as we have shown in the previous case. Okay, there's multiplicity here, a single electron is there, multiplicity 2, and here is 3 electrons, so 3 into half, 3 by 2, so 2 into 3 by 2 plus 1, so the multiplicity is 4. And now the magnetic interactions are here. This is 1, this is a ferromagnetic interaction, and this is also ferromagnetic interaction, and this is also ferromagnetic interaction. Okay, so all these interactions are ferromagnetic here. No antiferromagnetic interactions have been found. Why these are all ferromagnetic? Because you see, in each case, the magnetic orbitals have different symmetries. This is B2, this is A2. So orbitals have different symmetry. So spin should have same symmetry. Here also B2, B1, orbitals have different symmetry. So spin should have the same symmetry. And this is B2, A1. Okay, so orbitals of different symmetry, and spins should have the same symmetry. So in this molecule, calculation of ground state spin is also very easy, because we do not have to consider any antiferromagnetic interaction. So just sum of all the spins, so total 4 unpaired spin is there, and so 4 into half, so 2. So the multiplicity will be 2 into 2 plus 1, that is a 5. That is, it has a quintet spin, ground state spin. And naturally, we expect this compound as a ferromagnetic. Okay, so because only one possible spin state is here. So see, in case of copper chromium, the susceptibility is increasing on lowering temperature. So the compound must be ferromagnetic as we determined from the theory. Okay, so and these interaction paths can be assumed as a 2b2 and a 4b2 kind of interaction. Okay, now I will show you, now I will show you another example, which is our work basically. And in 2018, we published the work. We did publish one dinuclear, copper complex. And here, this complex was weakly ferromagnetic. Okay, so it was quite surprising because you see, whatever be the point group of the molecule, I'm not going to consider the point group of the molecule, whatever be the point group, and each metal center is copper 2. So the magnetic orbital at each metal center is same. Okay, and it is in the same molecule. So the magnetic orbitals are same, so the orbitals should have the same symmetry. And if the two orbitals having the same symmetry, the spins of the electron should have different symmetry, so that these two magnetic orbitals should interact in antiferromagnetic path. But surprisingly, the results show this compound was weakly ferromagnetic. There is one reason. The case is that the magnetic interaction, Pauli principle, what I discussed, this can be the interaction of the magnetic orbitals can be discussed in some another way, which is also in relevance with the Pauli's principle. So what is that? So you see, if the two orbitals having the same symmetry, then the two orbitals have some tendency to overlap. Okay, and as it has the tendency to overlap, then in case of an overlapped two orbitals, the single spins on each orbital should be one should be in upper headed and another should be lower headed, because this is actually Pauli principle. Okay, but if the case is that the two orbitals, if they are positioned at an angular distance 90 degree, okay, then it is a quantum mechanical calculation can prove that the overlap integral in that case of the two orbitals having angular distance 90 degree, how can we measure the angular distance? The angular distance between 2 points we can measure, just we can draw these two lines, and the angle in between these two lines is the angular distance between these 2 points. In the same way, the angular distance between these two metal centers can be measured if we just see the bridging angle. And if this bridging angle is 90 degree, then the overlap integral between the magnetic orbitals of this copper center and that copper center should be 0. That means these two metal centers should not have any tendency to overlap. As a result, as these two has no tendency to overlap, the orbital having the single electron should be in the same direction. Okay, so the interaction should be ferromagnetic. But in our case, the magnetic, the angular distance, that is the bridging angle, was not exactly 90 degree. It was 95.5 degree. That's why these two magnetic centers were interacted weakly ferromagnetic path. And now I have come to the last part of my lecture. These are the Prussian blue analogs that I have told. So far I have discussed is the work and the idea and the concepts of Professor Kahn. And now this work I have borrowed from Professor M. Verdaguer, is another famous French chemist. And he was also a student of Professor Kahn. And Professor Verdaguer did a lot of work in analyzing this kind of Prussian blue analog molecules. Okay. So what are they? I'm just coming to this. This is a Prussian blue. Everybody knows this is a structure. This is a formula of Prussian blue structure. And here is 2 iron centers are there, one with trivalency and another with the divalency. But from this molecular formula, we cannot assume the actual structure of the molecule. To know the actual structure, in this case, we have to consider this solid state geometry, solid state structure, where these 2 colored irons, one is iron 3, another is iron 2. And interestingly, you see, each of the irons, whatever way it is in iron 2 or iron 3, are 6 coordinated. Okay, you see this iron 1, 2, 3, 4, 5, 6, and this black iron, this is 1, 2, 3, 4, 5. So another will be there. That is another, Q will be in front of us. So this iron will also take the 6 coordination. So total 6 coordination geometries will be there. Coordination numbers will be there for each iron, whatever it is, iron 2 or iron 3. Now, what are actually the Prussian blue analogs? The color of this molecule is blue, that's why these are the Prussian blue, etc., etc. Then what are the Prussian blue analogs, analogous molecules? These are, if you just replace this iron 2 with a bivalent metal, that is a A2, and another, if you just replace this iron 3 with a trivalent, metal, that is a B3, then basically the molecules resulted are called the Prussian blue analogs. Okay, so this is a formula. So you have to keep it in mind that both the B3 and A2 are in hexa coordination, that is in octahedral ligand fields. And in this present discussion, we will take B as a chromium 3 and A as a iron cobalt nickel 2 with a divalent oxidation level. And these kind of molecules, the magnetic phenomena very nicely can very nicely be tuned with just changing this A. Okay, so this is the work, these 3 papers, we have taken this work from these 3 papers of Professor Verdeguer. Okay, and now what are these? And in case of B, we have taken it as a chromium 3. You see, this is a chromium 3, okay, having hexa, octahedral ligand field. So here the splitting will be T2G and EG type, which is a very familiar kind of splitting, and this is actually presented in the textbooks also. And now, just what happens, you are taking A2 as the vanadium 2. Okay, so what happens in case of vanadium 2? It's a D3. It has a D3 electronic configuration. So T2G orbitals containing these 3 electrons. Now, what happens when the magnetic interactions start? Here it is the chromium having the T2G symmetry, and this vanadium also have the T2G symmetry. So the orbital symmetries are same. So the spin symmetries will be different. Okay, so this will have antiferromagnetic kind of interaction. So each electron in chromium 3 will make antiferromagnetic interaction in 3 ways. Okay, this is a one, this is another one, and this is another one. So one electron is making 3 antiferromagnetic paths. So 3 electron will make 9 antiferromagnetic paths in this molecule. So the molecule will be completely antiferromagnetic. And the other molecule, which is, chromium 2. We have taken A as the chromium 2. And here, this is, is 1, 2, 3. Chromium has a 3 electrons, and here is 4 electrons. Here, 1 electron is in the EG state. Okay, so in the T2G state, as there was 9 antiferromagnetic interaction in the previous case, here also 9 antiferromagnetic interactions will be there. And the interaction with the T2G of this chromium 3 and EG of this chromium 2 is different because orbital symmetry is different. So the magnetic interaction will be ferromagnetic. Okay, so these 3 electrons each will interact with this electron in the EG, and there will be naturally 3 ferromagnetic paths. So 9 antiferromagnetic and 3 ferromagnetic paths will be there in this kind of molecule. If it is manganese 2, all the orbitals are containing 1 electron each, and these, these T2G orbitals will have 9 antiferromagnetic interactions, and it was in previous 2 cases. And in case of EG orbitals, 2 upper headed electrons is there, and EG symmetry is different from the T2G symmetry of this left-handed chromium 3. So one electron giving 3 ferromagnetic paths, as we have seen in the previous case. So 2 electrons in the EG state will give 6 ferromagnetic paths. Okay. And now if it is iron 2, this will be equal to, this way, this T2G, these paired electrons will not take part in any kind of magnetic interaction, and this electron and that electron, this will take 6 antiferromagnetic interaction with this chromium 3, and these two will participate in 6 ferromagnetic paths, as it was in the previous case with this chromium 3. Okay, if it is cobalt 2, so 2 paired electrons are there. These 2 will not take part in any magnetic interaction. This is a single electron will take part naturally 3 antiferromagnetic interaction with this chromium with the same logic as I have discussed so far. And these 2 electrons, these 2 EG electrons will interact in the 6 ferromagnetic paths with this chromium 3. And again, if it is nickel 2, all the T2G electrons are paired up. So no antiferromagnetic interaction is possible. Only unpaired electron is there in the EG system. So 3 plus 3, so total 6 ferromagnetic interactions will be there. And now in case of copper 2, all the T2G electrons and one of the 2 EG orbitals are paired up. So only one unpaired electron is one of the 2 T2G orbitals is there, and these will take part in 3 ferromagnetic interaction with this chromium 3. Okay, so only 3 ferromagnetic paths are there. So if you can see that in this way we can nicely tune the molecules from different kind of interactions and different kind of magnetic phenomena what we wish. Okay, so if we wish to design a purely ferromagnetic system, then this should be in this way. This way you have to design in this way. And if it is in this way, that is, if it is nickel 2, okay, so there also a completely purely ferromagnetic system can be generated. And if you use a vanadium 2, you can generate a completely antiferromagnetic system, and this way. These are all about my talk, and I'm thankful to my student Ornov. He has helped me a lot for preparing this presentation. And this is a photograph of the department where I am presently working. And thank you for your kind patience. And this is the view of our academic campus in a very recent time, in a rainy day. So thank you all.
Thank you, sir, for your very much nice and informative and very basic talk on magnetochemistry, basically magnetic interactions in the transition metal complexes, dinuclear transition metal complexes. Thank you, sir, for your for sparing valuable time to us. And I want to request the participants to ask any questions to us, sir. If you have any doubts about the theory, about the basic concept of magnetism, please ask yourself. Please unmute your, okay. Please unmute yourself and ask any doubt clearing.
I'm finding 3 chats. Is there any question? No.
No, sir. There is no question here.
Okay.
Okay. Participants are requested to unmute yourself and ask any questions. Students are mainly requested to ask questions.
Yes.
Students, mainly students are requested.
Designed for the students only.
Students only. Please, one question is written in the chat box. Why we use T2 and E in case of tetrahedral complex, but in case of octahedral complex, it is T2Z and EZ. Oh.
This is quite different question. Okay, but if you wish to get the answer, you have to go through the symmetry part. Okay, and what happens in case of these orbital splittings? You have to first consider the molecule itself and its symmetry. Okay, as the symmetry of an octahedral molecule is octahedron OH. Okay, so after doing the splitting, you have to check the character table of that octahedral point group, and there you will see. In the normal case, as you see in the textbooks, the T2G orbitals as the dxy, dyz, and dxz, you will see these orbitals in the character table have the T2G symmetry. And the EG orbitals, that is the dx square minus y square and dz square in the normal situation, these will have the EG symmetry. So this information is actually taken from the character table. And in case of tetrahedral geometry, the answer is same. Okay. So there lies the actual fact. So this G, T2G, EG, or something different, what symmetry will use, these all come from the character table. So you have to consider the character table to know the symmetry. There is no other way. Okay.
Any more questions?
Another question has come.
Another question, yes. For each electron, we get 3 AF or F depending on EG or T2G. Why the number is 3?
For each electron, we get 3 antiferromagnetic or okay. It is very simple. 3 antiferro. It is in case of mathematics, it is a case of permutation combination. Okay. For each electron, we get 3 antiferromagnetic or ferromagnetic depending on EG or T2G. Why the number is 3? Okay. Suppose there are 3 electrons I have shown. 3 electrons in the chromium. Okay. And if it is 1 electron in the right part, that is A2, okay, so each electron will interact with that electron. So the first electron in chromium 3 will interact with that electron on the right hand side. So this is a number 1 fact. The second electron in the chromium 3 will interact with that electron in the A2. This is the 2. And the third electron in the electron in the left hand side will interact with the electron in the right hand side. This is a 3. So these 3 paths are possible. So if there are 2 electrons instead of 1, definitely the path will be 6. And if there are 3 electrons, unpaired electrons, definitely the path will be 3 plus 3 plus 3. So it will be 9. Is it clear? Dhruvo Datto. Are you student or teacher? I don't know actually.
Dhruvo, please unmute yourself and
interact. You can talk.
You can interact. You unmute yourself and interact with the
student from which institute? Dhruvo.
Dhruvo from which institute?
Yes, sir. I am student.
Student from which?
Sir, I am from Rohada Ramakrishna Mission, Ramakrishna Mission, Vivekananda.
Okay.
Ramakrishna Mission, Vivekananda Centenary College, Rohada Ramakrishna Mission.
You are the PG student or UG? Dhruvo? Because in 2019,
Dhruvo,
in 2019, I had a visit to your college. I delivered a lecture. Did you listen to this?
No, sir, I am from UG.
Okay.
UG na PG?
I am from UG Zoology, second year.
Oh, UG Zoology. Okay. I came to the chemistry department actually. Okay.
Okay, UG Zoology.
Any question?
Any more question? No. Any more question? No. I have one query, sir.
Sure.
You have mentioned that for dinuclear metal complexes, if we have trinuclear or polymeric metal complexes, then can we study the magnetic interaction study of these complexes?
Yes, definitely we can study. But
what type of observation?
Yes. As the nuclearity is being increased, the system is being much more and more complex. Okay. So in case of trinuclear system, you see, in case of dinuclear system, we are considering the interaction between the metal 1 and metal 2. And if this is a trinuclear, then we have to consider the interaction between 1, 2, 2, 3, and we have to find if there is any interaction between 1 and 3. If that is there, this should also be considered. Okay. And not only that, if the nuclearity is 3, not necessarily the molecule will be linear. It can have a trigonal geometry. If that is the trigonal geometry, then the 1, 2, 2, 3, and 3, 1 interactions should be considered. And if it is a tetra nuclear geometry, in this way, as we will increase the number of metals, the interactions will increase, and this interaction will be in much more complex fashion. And in those cases, it is very much difficult for higher nuclear complexes to explain all these things in this way as I did it. There we have to use some softwares. Okay, different softwares are there. They are actually analyzing this structure magnetic correlations. Okay, so but the basic thing is that what I have discussed. In this way, we can do it, but it will take much more time. Okay, but the main thing, the main basic ground is same that I have discussed.
Okay. So if there are non-covalent interaction in the molecules, then they have some effect on magnetic properties.
And definitely
non-covalent.
Definitely. And actually, in case after the development of supramolecular chemistry by Professor Lane and others, Pedersen, they got Nobel Prize in 1987. Lane, Pedersen, and Pauli. So after the development of supramolecular chemistry, and there is one kind of interaction is there, one kind of molecules is there, is coming, and those are named as the super duper molecules. That means the supramolecules are the molecules having only magnetic interactions. Molecules having non-covalent interactions. And the super duper molecules are the molecules which are composed of not only supramolecular interaction, but also magnetic interaction. So in combination of these two interactions, the molecules resulted are sometimes known as the super duper molecules. But these are very rare, but a number of magnetochemists all over the world, they are studying this. Okay, so I think this will be very important in very near future.
Okay, thank you, sir. Participants, if no more questions from you, then I wish to vote of thanks. Give vote of thanks. No more questions, participants.
Rajmallo Bishwas. Oh,
nice.
Rajmallo, you just asked a question. First question. You are from which institute, Rajmallo?
I am from Tripura University, sir.
Which university?
Tripura University.
Tripura?
Yes, sir.
Tripura University.
Okay, that is in Surjamuni Nagar.
Yes, sir.
You are from chemistry?
Yes, sir.
So where you are living in Agartala?
Yes, sir.
Okay. So really different institutes from different country, different states are present here. It's very fine.
Okay, sir. Actually, many of them are in YouTube also. Here.
Yes.
Okay.
Yes.
But I no question in YouTube chat box. Okay, so let us conclude the program here. First of all, I would again wish to thank you, sir, for your giving consent to deliver a lecture in this platform in front of our interdisciplinary subject students, mainly from their chemistry, zoology, and biology. Mathematics. So thank you for delivering a lecture on such a very interesting topics. Basically for the student of chemistry who want to know the magnetic interaction, not only chemistry but also physics, but also zoology. You mentioned that zoology also can use this magnetic interaction. So thank you for delivering such a basic concept of magnetic interaction between the metal center and metal ligand bonding also. We wish to see you in the next time also in the future time to interact with you by our students. Thank you, sir. Next, I wish to convey my thanks to chairperson, our principal, Dr. Sapon Kumar Mishra, who always encourage us to apply for this type of courses and arrange some extraordinary works which will develop the personality of the students besides their academic development. So thank you, sir, for your constant encouragement. Next, I wish to thank our Department of Biotechnology, Government of India, for generating our financial support for organizing this type of summer training school. Not only school, but also some hand-on experiments for creating interest of the students into the life science and biotechnology educations. So thank you, Department of Biotechnology, Government of India, for awarding a prestigious scheme, DBT Star College scheme, to our college. And next, I wish to thank our joint coordinator, Dr. Soma Kormokar, HOD, Department of Zoology, and Dr. Kalipodo Maiti, HOD, Department of Mathematics, and also other colleagues who are still present in the platform. And finally, I wish to thank our participants for without whose support the program is meaningless. So thank you, the participants, all the distinguished participants from all over the institutes. Thank you for your constant support to make this program successful. With these few words, I wish to officially end the session of today. We will meet again tomorrow on at 11 a.m. On 23rd July. Thank you all.
Thank you very
Okay,
much.
thank you, sir.
Thank you.